Yeah.
Picture this here, with us Bigfoot whip. Okay, I got it, Jim. You get your soil.
And Dave, did we get a back number for the frag?
187.
Thank you.
It must be 186. I got 187 for the soil.
Roger. Agreed.
Get it, Libby. Okay. Bitch, there's a bag. There's a bag. Okay, if you could hold on to this little one, I'll roll up the big one. Okay, the next thing on the agenda is a double core. Yeah, okay, I'm gonna over-configure for it. Okay. Hey, Joe, we got a crater that looks sort of fresh up here. 100 meters or so, looks like, with a fairly fresh rim. Would you like a double core in the rim of that, or would you like us just to pull it right here?
Stand by.
There's a change of albedo on the rim. It's much lighter.
Roger, Dave. Drive the core right down to the rim.
Thought you might say that. Okay. Take some of this stuff back and we'll have to walk up there. But that won't take too long.
You were just checking up on us.
Okay, Jim, you got everything you need and I'll just come up there with you. Yeah, come on up here and I'll get the cores out. Okay, here we go. Head up to the crater. Think we can get there without any trouble? First one right here, you mean? I'm thinking of that fragment. It'll probably take a good 5 minutes to get up there. Yeah, you're right. Now we can push them. Yep. Joe, I guess we'd take 5 minutes to get up there. What do you think?
Negative. Drive the core where else you think might be convenient.
Oh, we got a good place here. We got a fairly deep crater. It must be about 10 meters across and 1.5 meters or so deep. And we'll pick the rim of that. There's a fresh impact crater in the rim anyway, which looks like it pulled out some. Let me get it. Is that good enough place for you, Jim, right here? Sure is, Dave. Okay. I wouldn't want to go up much farther on this slope. It's too hard to get up. It sure is, isn't it? Make the bike kicking too much. Well. Okay, let's have it a double core here. There we go, a double core. Hey, Jim. Huh? Oh, you hear me? Why don't you turn around this way? I just got to grab the cord. I'm going to take location shot. Oh, okay. I think you'll get location. Hold that line while I get the cords out, okay? Hey, Dave, if you hold. Okay. Hold on, one while I get the upper one in. Roger. Engine handle. Hey, Joe, the boulder we just sampled is the only one of its size anywhere to be seen. There's a fairly fresh crater up a little ways, maybe another half a kilometer or so. We can ring off. We can that off. Save that part. Yeah, they might want that, huh? Get on the other side, yeah. Push it in from the uphill side. Yeah.
And Dave and Jim, as you're getting a double core for us there, we'll be wanting to leave the station in about 10 to 15 minutes. We'd like only the big camera photograph following this. I think we're in good shape on everything else.
Okay, Joe. That's fine. Push it, Jim. That's as far as I can push it. I got the picture. Go ahead. Hey, we got one full core. Second core is going in about 2 inches per hammer stroke.
Roger.
And we've got almost the second core. Got another couple inches to go, Jim. Doing good.
Jim, you're an Iron Man.
Thank your finger. Oh, the boss is. Okay, that's good, man. All the way in. Good show. Okay. Let me come up to the hill there. I got the picture. Okay. Pull it out very gently. Nice, nice. Does it. That's nice. Coming out very clean. Looks clean. Hold it steady. Got a good one. Okay, come on. This way. Cap port. Looks like we have some rings on the cap. Okay. There, pick the cap up, put it on there. Okay, good idea. Oh, we gotta ram it first, Roger. Let me put your hammer away. Ram her out. Okay, why don't you just hold it? Okay. That's right, feel pretty hard? No. Okay. Rammer went in about 6 inches. Okay. Yeah, just don't break it. Break. I'll try to break it. Attaboy. Easy does it.
And Dave, we're standing by for a number on the core.
Yeah, the top one is 03, Joe. Oh, don't lose the core. Lose the core. Huh? There's a cap there. Can you just do? Yeah, I got another one. Don't sweat the caps. We got buku caps. Okay. I'm gonna let you. God, listen. Don't lose the core. See ya. You can hold this one. I'll put the cap on the bottom one. For new caps, you know, they're a lot harder to get on. Seen those before. Can you show the numbers on? Yeah. I gave you the top one. I can't see the bottom's too dirty. Rub it off when you get going there.
No problem on the bottom, Dave. We know that.
Okay. I give you this. Okay. I'll put this in your pack. You gotta ram it. Front of that. Golly, that's a little bitty to do. Okay, turn right so I get the rammer. Okay, it's rammed. coming back. Okay. Now try and recover those caps.
Yes, Jim, if you could with the tongs, we'd like it back.
Yeah, we'll try. Yeah, those new caps, Joe, with a metal band on them, will sure stay on a lot better. Okay, I want to here, I'll hold them. Core. Okay. Can't even see them now,
I
right?
understand.
They're right here, Dave. Right under here. I can see the edge of it. Found any conch? Yeah, go get them. Just a minute. Slow down. Ooh, I dig in pretty deep.
And Jim, we'd like a stereo pan with your 70mm camera. Maybe now's a good time to get it. Or wherever you think it's a good place.
Okay. Look at his hands, Joe. Your finger. You can take a picture. Okay, partner, where are they? Right in here. Oh, yeah. You hold this, I'll put it on. Okay. Okay, I've got it. We see you're carrying the ignition key there for the rover. That's right, that little blue thing. Radar Nova's pretty dirty, unfortunately, Joe. There's no way to keep that color chart clean with all this stuff.
Roger.
Gotta have a little moving base on that band.
Roger, Jim.
Try and get it, no problem, stolen. You know, blurred picture isn't much good. Okay. Take off the lens. Cap.
Good go.
Nice step. Going. 500. Okay, Joe, I'm gonna give you, looks like I got some pretty good contrast looking up to the northwest. I'll give you the far side of the rill, the vertical and the horizontal. And I'll use a, let's see.
Sounds good, Dave, and we'd like about 2 minutes worth of pictures and then think about leaving.
Okay. That's a 250 and an 8 look to you.
Sounds good.
Okay.
Okay. Hey everybody. Yeah, I know. I remember that. I don't know how I do. I remember that. I remember the whole conversation between them and everything. Yeah, that whole chapter was like, oh, but you'll get hacked if you do this. So then we do this. But then you can do this to hack into that. So then we do this. And it just keeps building and building and building. At least that's how it was in the 6th edition. It was very like, alright, well this isn't gonna work, so let's do this. And then this isn't gonna work, so let's do this. Over and over and over again. That was the whole chapter. Hi everybody, what's up? What is up? How is everybody going? How is everybody doing? I need to reactivate my brain here. I turned off my brain after work and that's no bueno. Ah! I need water. That's what I need.
Very interesting outcrop over there, which looks like vertical joining in a big block with a
Anyway,
horizontal.
we'll get started in just a second.
Block must be
I gotta make sure everything is set up.
and it must be about to go twice that across with a layer maybe 1/4 of the height of the block, and I got a 500 of that. And I'll also take you a 500.
What are you saying, Mink? What are you saying? What are you saying?
Roger, Dave.
Lots of math today. Lots of math. Lots of really fun math.
Back towards the limb. We're going to eliminate Satan 3.
Okay.
Still going over my notes a little bit. That is hilarious. Absolutely hilarious, Meg. So funny. Just great. My note packet is like twice the size of last time. That's no good. A little bit of geometry, a little bit of algebra, a little bit of calculus here and there, a little bit of vector work, a little bit of fudge, a little bit of patch ups because
Thank you, Jim. Good call.
she's not. I don't think she is. I think I'm in the clear. I've got one button from work still, so I need to keep it conservative at work. And since this is a formal lecture, well, not super formal, I want to keep it classy. Anyway, I was reading through the textbook over the material that I wanted to show today, and, well, same thing as the first lecture. I looked at some of the stuff, I read through it, and I'm like, oh, nice, this is neat. And then I finished that portion of the chapter, and then I thought to myself, yeah, there's no way that I'm going to show any of that on stream, or I'd be here for 4 hours. Put on your tux, yeah, do it. So, I had to fudge a few things. I think 2 places in specific, well, one right off the top of my head. I'm going to make an assumption, and you are just going to have to deal with it. I'm not going to explain it, because I will be here for a couple hours if I do. Well, I plan on being here for a couple hours. I would be here for a couple hours more. Anyway, there are a few assumptions in here that I'm going to make. And you might ask, why are you making that assumption? And to that, I will say, don't worry about it. Because I am not going through all of the hassle of deriving that. I will in the future, but I'm not doing that on this stream. We've got tons of math to go through today. Tons of awesome math. Whatever, Mank. I don't believe you that the sky is up. Boom. Take that. Yeah, but this is gonna be lots of math. It's gonna be a lot of fun math. And by the time the lecture is over, we will have derived the equation for orbital energy. Pretty cool, right? The enemy gate is down. My gate is math. That's my wall. It's a wall of math. Still don't believe you, Mank. I think you're wrong. I think you're wrong. Sorry. I'm gonna give people that aren't here yet a few minutes to trickle in. I'm just about all set up, but these lectures are always difficult if you don't catch them from the beginning. So I'd rather wait. I'm the kind of professor that will wait until all the students are here. That's just because I'm a nice guy. I just see question marks, Mank. What does it mean? Oh, never mind. Chatty can't handle those. Interesting. Interesting.
Like a little piece of glass right there.
I'll have to upload, yes I will. I'll have to upload this information to the drive when I'm done, so you guys can take a look at it. Did you guys have any questions from last time?
I can get up the hill to it.
I seem extra tired today. It was a pretty long day at work, man. I definitely need to perk up a bit, though. It's a little bit high. I'm going to be turning it down for the lecture anyway, so I might as well just turn it down now. Yeah, I need to perk up a little bit. I had a really long day at work. Once I get into the math and whatnot, once I get into streaming, then I'll be fine. Well, that'd be cool, Kelly. This is my magic school bus. It's my magic school shuttle. Sure, let's go with that. My magic school shuttle. Cause why not? But thank you for letting me know, Mike. Okay, crap. I don't have energy drinks, but I don't feel like making a whole cup of coffee. Ah! Do I have anything that has caffeine in it? Well, what time is it? It's 7. Should I risk it for the biscuit? My roommate from college used to just take scoops of coffee out of the coffee bin, just coffee grains, and just eat them. I know, that's what I was thinking, Mike. I was thinking I should probably just go make some tea. Maybe I'll go make some tea. Because that's light on caffeine, right? You know what? I'm gonna do it. I'm making tea. I'll be right back. It won't take me a second. Yo, tea party! Yeah, I could have done chocolate. Espresso beans. You eat straight espresso beans. Whoa. That's wild. Doesn't matter what kind of tea party. It can be our own tea party. It's fine. Okay, we should probably get started. So I'm not here all night doing a bunch of math. So far, no ulcers. Well, so far so good then. Okay, let's go like this. Whoa, streamception. Alright. Alright. I'm here. Okay, draw. So let's recap, right? Recap from 001, or front matter. What did we learn in... Oh, it's not 001. Excuse me. It was 000, technically. Because it was front matter. Hey, Simclept, what's going on? Alright, so what did we learn? Just gonna go through my notes and see what we learned. We went over what STEM is. STEM... Right? We talked about a few philosophers as well. We said the following. The universe is not math. Right? The universe is not math. Math is just a model for it. Math is just a model for the universe. The universe. And models change pretty often. And models change. And models change. Okay? Is the thing that holds a flower up? No. No, not quite. Not quite. Well, the universe is not math. Math? Is my shirt getting all wacky? Hold on a second. Let me check something. I want to make sure that my stream isn't... Oh, never mind. The shirt's fine. Okay, I wanted to make sure my shirt wasn't being chromed out or anything silly like that. Alright, so universe is not math. Math is just a model for the universe. We talked about the difference between Plato versus Aristotle's view, right? Plato versus Aristotle and their views. Alright, next what we did was we talked about Newton's 3 laws. Right, so Newton's 3 laws. Newton's 3. Newton's 3. Which were the law of inertia. Anything at rest will stay at rest, and anything in motion will stay at motion. The law of force. Well, I can actually just write this one out, which is equal to mass times acceleration. And then we learnt equal and opposite, right? Those are the 3 laws, equal and opposite. And yes, order matters here. This is 1, this is 2, and this is 3. The order absolutely matters there. Okay, then we took a look into Newton's second, right? Newton's second. And we basically said this. MA, right, is really the derivative with respect to time of your momentum, right? Where MV is equal to P. Okay. Okay, that's all I'm going to talk about there. And then we went over Cartesian systems. So Cartesian systems, which are like, you know, X, Y, Z coordinates basically. And vectors have can take on Cartesian, what are called components, which are just the different components of a vector. Okay, and then what did we do next? We modeled an ICBM. Okay, modeled an ICBM. Whoa, ICBM. From USA to Puppy Kitten World. And it was very successful. Everybody made it there. All of the puppies and kittens made it all the way there. Go them. Okay. Cool. We're going to talk about orbital energy today, okay? Orbits and orbital energy. So, orbits. Oh. So, I'm just going to do orbits part 1. Orbital energy. I really should have done that in a different color, but oh well. Hey, Kerbonaut. How's it going, man? Alright, orbits part 1, orbital energy. Let's see, my tea is almost done, so I think we're going to wait until that's done brewing before I get started here. Did you guys have any questions about any of the stuff that we went over last time? Again, we went into like a really extensive example on the ICBM, and we didn't actually finish the equations of motion, but we got close enough, so I'm not going to worry about finishing those today. But again, if you guys have any questions, just let me know. Anyway. Alright, so let me go get my tea. I think it's basically done now. Guys, does it sound okay now? Can you hear me alright? Alright. Oh boy. Got my tea. Oh, alright. Alright. You guys ready? It's not going to start with math. As always, I'm going to start with philosophy. Because philosophy was science before science had its own name. So, I'm going to start with a few philosophers and a few astronomers. And it's also tea time. Tea time. Hey, it's kind of see-through. That's cool. It is tea time. Alright, we're going to go over 2 astronomers today. Well, 3. But 2 in a bit more detail, okay? And to start, we are going to go down to the right part of the page, please. We are going to travel all the way to Europe, or Egypt, not Europe, Egypt, Egypt, and we are in the time period around 100 AD, okay? There was an astronomer, an Egyptian astronomer, and his name was, and I know I spelled Egypt wrong, his name was Ptolemy, like this, Ptolemy, that was his name. And he was an Egyptian astronomer, and he came up with a few models. And the models were basically simple, right? The model was like this. Ha! Funny, Novus. Hilarious. And I'm mad and sad. I guess that would be something to be mad and sad about. Well, this won't teach you how to get to orbit in KSP. This will show you how to get to orbit in real life, but not in KSP. You're in denial. Not all the way in denial, just next to denial. All right. So the Ptolemaic system, right? The Ptolemaic system, or the Ptolemaic solar system, rather, was based on a few assumptions, right? You guys have some pretty wild kappas going on there. Ptolemaic solar system was based on a few relatively simple assumptions, right? God is perfect. Whoa. He said God is perfect, but my spelling isn't. Therefore, orbits are perfect. Orbits are perfectly circular. Oh my. Wow. Therefore, orbits are perfectly circular, right? Because the gods, there's no way a god would make anything that's not perfect, right? It just wouldn't make any sense. So, of course, the orbits of the planets are going to be circular. That would only make sense. And there was another assumption that he made, right? Since God created Earth, right? God created Earth as sort of God's child, then Earth must be required to be the center of everything. Is center of everything. Every single star in the galaxy and the cosmos and every single planet in our solar system must be revolving around the Earth. That's the only thing that makes sense, right? Because humans are everything. If God created us, then clearly we're the center of attention here. So the Earth is the center of everything. Of course. I mean, that obviously makes sense, right? Obviously. Well, here's the thing. He based an entire solar system model off of this, all right? And his model used 3 components, all right? His 3 components were this. Vain Earth. Too cute, Sai. Too cute. Yeah, clearly he was. Anyway, his solar system model is based off of 3 components, all right? And the 3 components were these. The first component was called an epicycle. The second component depended on the Earth being slightly offset from the center of everything, but it still is the center of everything. And the third component had to do with something called an equant, or an ecant. And here's his model, right? So he had the Earth. Well, I'll go like this. He had the center of the solar system, right? So solar system center. And then what he said was this. He said the Earth isn't totally all the way right there. It was just a little bit offset, right? He said the Earth was like right there. It was close. It wasn't all the way, but it was definitely close. And then, right? So it's not exactly right in the center. It's just a little bit off, though. So let's go like this. Let's take another component, and let's go like this. Let's say you're looking at Mars, right? Let's say you're looking at Mars. Then Mars is all the way out here, right? And that's the astrological symbol for Mars. So I'm going to try to be using astrological symbols here as much as possible. Basically, his model for how planets revolved around the Earth, because of course they revolved around the Earth, was like this. They all evolve around a center point called, well, I'll go like this, called the ecant, or the equant, for that specific planet, right? And then the other thing about this is, okay, so let's say the planet is going around town like this, right? So that's the orbit of the planet. But the orbit, the planet doesn't follow that line exactly. The orbit follows what's called, the planet follows what's called, an epicycle, all right? So this is called the epicycle. All right, so you've got the solar system center. You've got Earth, which is slightly offset from the center, because Earth has its own equant from the solar system center. And then so does Mars. Mars has its own, right? Well, they are, Kelly. See, oh, shut up. Yeah, this is meant to be a circle. This is meant to be a circle. I'm not a god, okay? The equant is slightly off-center, right? And then this entire component rotates all the way around at the same time that the planet rotates around its epicycle, okay? Both of those are at different rates, okay? How accurate do you guys think Ptolemy's solar system model was? Just a question. How accurate do you guys think it is? I'm not talking about my drawing. I'm talking about how accurate you think his system was. I'm not a god. I can't make circular orbits. How accurate do you think his... Yeah, you know what? Y'all are just... I can't do it. I can't do it. I want to give you guys a decent orbit here. There. Get over it. Get over it. He got circumference pretty. He got the circumference pretty well. Yeah, guys, this model, if you adjust everything the right way, this model is actually pretty damn accurate. That goes to say, everything in the universe is just a model. Okay, it's just a model. It's not exactly the universe. It's just a model for it. This wasn't too far off. Okay, he was able to match all of the data that he had pretty closely. So fun fact. So that was Ptolemy's model. But then someone else came along. Exactly, Meg. It was very good at predicting where things are going to be, and that's all they needed. So in his eyes, like, that's exactly how it worked. Okay? So let's do some time traveling. Let's go forward to 1543. 1543 AD. And that was basically the go-to model for a while, right? An astronomer named Copernicus releases a publication just a few years before he died, or a year before he died, okay? Yes, exactly, Novus. And the name of the paper was this, and I don't want to spell it wrong. It's De Revolutionibus Orbium Coelestium. All right, and this translates to on the revolutions. Nope. It translates to on the revolutions of the heavenly spheres. That's what it translates to. On the revolutions of heavenly spheres. No, hail Copernicus, man. And his model was basically this. He said no, all right? Ptolemy was wrong, okay? Ptolemy was wrong. The Earth is not the center of everything, okay? The solar system, in fact, maybe someday I'll be able to spell, solar system is heliocentric. It's heliocentric. Okay, everything revolves around the sun. Revolves around the sun. Okay? You guys are ridiculous, you know that? You know that you're flat out ridiculous. It's heliocentric. Which means, right, well, oh, there's one more thing. He also still used epicycles. Still used epicycles. So it was pretty similar to Ptolemy's model. It's just the center of the universe was a little bit different, right? So now you have the sun as the center, and that's the astronomical symbol for the sun. And then you've got all of your planets rotating around the sun now in their own epicycles and their own orbits as well. So the Earth would be, you know, right there, for example. Well, I had another planet in there. Actually, no, I'm not going to do that. Well, yeah, I'll do that. I can't be ridiculous. I'm quiet. Yeah, I know. You're not ridiculous. I'm just kidding. None of you guys are ridiculous. Sorry. It was, again, it was on an epicycle, right? So it actually rotated around a point that rotated around the sun, like that. Okay, it was still on an epicycle. So it was a heliocentric model, but it was still using epicycles. And I'll just make another note there. That's the epicycle. Okay? But it's a little bit closer, right? Alright. That was Copernicus. Let's see. The church. Whoa. The church did not like it. In fact, nobody liked it. Nobody liked it at all. Everybody basically said, look, are you crazy? Like, it's pretty obvious that the Earth is the center. Like, we already have a model. Why are you just trying to change things for your own benefit? Doesn't make any sense. Nobody was on board with him, you know, within reason. So for a while, people were debating, like, what the best way is to explain an orbit. Yeah, exactly. Exactly. It was called an epicycle. And they didn't know what gravity was. They had no idea what nobody understood gravity. Nobody used the term gravity back in the day. They didn't know what gravity was. That's why they were able to do this. They basically said, hey, this is fine. Like, there's no such thing as gravity. And it's, again, they weren't saying there's no such thing as gravity because they just weren't talking about gravity. Nobody knew what it was. Come the 1600s, our third and final guest astronomer today, I guess. His name is Kepler. Some of you may have heard of him before. He was another astronomer from Germany. And he came in and he basically said, yeah, exactly, Kelly. That didn't happen for a while. I know. That didn't happen for a while. But Kepler came along. I'm so glad he did. Made everybody's lives so much easier. And Newton, sorry, not Newton. Kepler basically said the following. I'm paraphrasing. I wasn't there for it. You're all wrong. Okay? He had extensive observations from another famous astronomer named Tycho Brahe. Okay, Tycho Brahe put a lot of this stuff together. Go ahead and prove gravity. Go read general relativity. That's Einstein's job. That's not my job. Anyway, he got this from all of these observations that Tycho Brahe put together. And Tycho Brahe was trying to prove his own solar system model, which was also wrong. And Kepler was Tycho's student. And Tycho basically said, oh, I'm going to die soon. You need to finish my work and prove my model. And Kepler is like, oh, yeah, I'll do that. No problem. And Tycho Brahe dies. And then Kepler looks at Tycho's work and says, yeah, this is all wrong. So Kepler started from the ground up and completely eradicated everything that Tycho Brahe worked for in his solar system model and came up with his own. And his own model is dependent on 3 laws. 3 laws of the Keplerian model. And the 3 laws are as follows. Law number... Well, I'm curious if any of you guys know, actually. Do any of you guys know what the 3 laws are? Yeah, right? Hats off to the student there. He basically said, no, you're all wrong, but I'm going to take all your work now that you're dead now. Do you guys know any of these laws? Any of the 3 laws? Any of 3 of Kepler's laws? And if you look it up on Google, I'm going to know. Yeah, I know, right? Yeah, I know. I was waiting for Meg. I know Meg's going to use Google. Alright, if you guys don't know, I'm just going to write them down. First law. Orbits are ellipses, not spheres. Sorry, circles. Orbits are ellipses, not circles. There you go. Something to do with orbits. Demonata, you got it. And that is the second law, Mank Sauce, yeah. An orbit will sweep out equal amounts of area in equal amounts of time. Whoa! Equal time for all orbits. Wait, for all points, rather. For all points. Okay? Scholarly articles. I think you'll have to be a bit more specific on your Google search there, Novus. And the third one is the following. The period of an orbit squared is directly proportional to the semi-major axis to the power of 3. Those are his 3 laws. Pretty straightforward. And we'll be going over those laws pretty extensively later. An important thing to note here, guys, at this point, we still didn't know gravity. Okay? Kepler derived all of these without even knowing what gravity was. He derived all of these, and he got them spot on, too. In fact, people were so interested in his work that Newton later on, Newton literally derived these statements from math, okay? So, hold on, statements from math. So what happened is that, again, Kepler came along and he said, look, I know that these things happen. I don't even know the math yet, but I know they happen. And then 100 years later, or 200, I think, Newton comes along, develops the math to derive this, and basically says, yeah, checks out. So Kepler was able to do this before the math was even invented to do it. So that's pretty cool. Okay. I don't know if I want to do this part. Do I want to do this part? Yeah, probably should. Yeah, I probably should. Okay, let's take a look at orbital energy, alright? And to do that, to start, we're going to look at first energy of 2 particles, okay, of 2 particles. Okay. When I say particles, what do you guys think I'm talking about? Because I'm not talking about particles. I'll tell you that. So we've got one mass here, right? So let's take a look. Let's take a look at forces here. So we've got one mass here, right? So this is a mass. We'll call this mass M1. We've got another mass too, right? There's 2 masses here, M2. They're separated by a distance r. Okay, that's the separation from one mass to the other mass. And then, aren't we going to hit Galileo? No, see, Galileo was in the textbook. I could have gone over him, but it didn't pertain directly to... Alright, well, he did, kind of, right? The thing that Galileo proved was... Everybody thought that if you had something orbiting around you, then you could not be moving yourself, if that makes any sense. What Galileo proved was basically, no, this is wrong, right? Because he was able to use a telescope to view Jupiter's moons. And he said, well, Jupiter's moving around us, or the sun, or whatever it was. But Jupiter then has things moving around it, okay? So that disproved that theory. Galileo was famous for publishing most of his work in Italian, which was the common language, whereas at the time, all scholarly articles were written in Latin, because that was sort of the high language, and if you were scholarly, then you would learn Latin to read these. But he wrote it in the common tongue so everybody could understand it. Pretty cool. His work was in the form of a debate, where two people were debating each other, and they were debating the Copernican and the Ptolemaic models. And it's really funny. The person that took the side of Ptolemy, he named Simplicito, which in Latin, right, in the high language, was actually the name of one of Aristotle's greatest future workers, somebody that continued to work on his work, Simplicito. However, in Italian, Simplicito means idiot. So... I don't know. There were a lot of cool things about that article. But anyway, so we've got two masses, right? We've got a force. Well, I want the force to be red because I like red force. We've got force of... force going from 1 to 2. I'm going to go with that notation. And then we've also got the force... going from 2 to 1. Just like that. Okay? Which force is larger? And I'm asking you guys this. Which force is larger? F12 or F21? Which force is larger? And if you get this right, then 300 space coins are going into your pocket. Because the system is so inflated already. So, which is larger? The force on 1 to 2 or force on 2 to 1? Not Nick says F1 to 2. Kelly Johnson is fooling around. Demonata says F1 to 2. Manksauce says, aren't they the same? Yes, they are. Oh, Novostatic, you were just too late. In fact, these two forces are exactly the same, okay? Nope, Tiger Shark, these forces are exactly the same, okay? If you jump up into the air, and you know how, like, the Earth is really, really intense gravitationally, you can't really escape it, and Earth is putting a lot of force back down on you? Fun fact, okay? You're putting just as much force on the Earth that the Earth is putting on you. Nice. Oh, get out of here, Kelly. Anyway, yeah, the forces are actually the same. So whenever you're jumping up on the ground and the Earth is pulling you down, you're actually pulling on Earth at the same exact intensity. It's just that the Earth doesn't seem to feel it as much because the Earth is a lot larger than you. Okay? Sent to Ted. Yeah, get out of here. They're the same. They're the same. And what is this force? We actually know this force, okay? Nothing. You don't get a consolation prize, Nose. Mank beat you to it. No way. And you've already got plenty of coins. Oh, actually, Mank had way more than you. Whatever. Give yourself candy. Anyway, we know this force, right? So, ooh, harsh, harsh. And we know F1 to 2, the magnitude of this vector, is equal to F21, the magnitude of the other vector, in a two-body system, is equal to G M1 M2 over R squared. Okay? And we know that's the force, right? So we're going to abstract the heck out of this thing, all right? And we're going to make it as baseline as possible. And it's going to look like this. It's going to look like this. What we want to solve for, right, is the force of one body acting on another. But in order to do that, we have to put that in three-dimensional space, okay? And this is where it's going to get a little bit math intensive, so I apologize. Just try, okay? Just try. We've got our Cartesian system. I wish there was like an easy way to draw a straight line, but you know, guess that's too much to ask for. We've got M1. Actually, let's go like this. We've got M1. M1 is going to be the big mass. We've got M1, and we've got M2. And these guys are stuck in inertial space somewhere, right? They're just kind of floating out there. And here's the position vectors of those two things with respect to an inertial frame, right? So this is I hat, J hat, and K hat. I'm just, it's the same thing as X, Y, Z. I'm just calling them I, J, K. Demonata, don't worry about it, man. I don't expect you or any of you guys to fully grasp all this stuff. This is going to be a little bit over your head. But I wanted to show you the process behind doing it. And so you have it in your notes, right? Now, the vector to get from the inertial center to M1 is going to be capital R1. Same thing with M2. It's going to be capital R2. Okay. Hey. Just like that. Okay. Now, let's take a look at, well, let's see. What is, let's go like this. What is the position of M2 with respect to M1, right? That's going to be R2 minus R1, which is not that. That's not a vector. It's going to be this, right? And we're going to call that lowercase r is equal to R2 minus R1. Okay? Yeah, I don't think the derivation was in physics 1. Cuz I'm going like baseline, like this is the derivation for it. Anyway, so this is it, right? So we've got no, not R2D2. Anyway, right? So this is R2 and this is R1. And this is the difference in between them. This is the difference vector. This is what happens when you subtract one vector from another vector. Just like that. Yeah, Novus, I feel like it's not... I feel like some people take it for granted. I mean, I know I totally do, but not everybody knows calculus. Anyway, so this is the vector difference in between them. R2 minus R1, okay? Now, we have this, right? So we got then, we have this equation. R is equal to R2 minus R1. Okay? Those are accelerations, right? Sorry, they're positions. If we take the derivative, and Demonata, don't worry about this too much, man, I'm telling you. It's not worth getting all of this stuff down right off the bat. That means we can go like this, right? We can go like this. We can go like R double dot, the double time derivative, or the acceleration, is equal to the acceleration of 2 minus the acceleration of 1. All right? So in order to get this, we need to find these two, right? Right here. So what are these? What are these? Well, I'll tell you. We're going to derive them. So we need R2 and R1, right? We need the acceleration of this, and we need the acceleration of that, okay? Well, the acceleration of this is going to be pretty simple. So whatever this point is, right, it's probably going to be accelerating towards the other body. That would just kind of make sense, right? And again, we can use the equation for force, gravitational force, right? So let's draw our force vectors real quick. Again, this force right here is F21. And this force right here is F12. Which are the same magnitude-wise, but they're in different directions. Oh no, Demonata, you're not, man. It's anybody can join and like learn from this. It's not really a time and place kind of thing. And even if you're not learning, dude, you're here to just talk, and that's totally fine too. You're here to talk and ask questions. Just don't forget to ask questions, you know? So anyway, we've got these two force vectors, right? So let's draw those out. So we know F21 is equal to mass of 2 multiplied by the acceleration vector of 2, and that's equal to this. G m1 m2, I'm just using Newton's gravitational law right here, over, right, gm1 m2 over r squared, which is this magnitude squared, right? So let's get that magnitude, which is just r2 minus r1. Well, it's assumption number 1, okay? This is the scalar, this is the scalar version of this. If you want to put it in vector form, you're going to throw another cubed down here or another power down there, and then you're just going to multiply it by that vector. R2 minus R1. All right, so again, R2 minus R1 is this vector right here, right? And this is a negative, sorry. The force is negative, don't forget about that. The force is negative, right? So this right here is this direction, F21. That's what we're solving for, F21. It's going in that direction. And it describes the acceleration of R2, right? Now let's do the same thing for F12, right? So the force from 1 to 2 is equal to M1 R1 double dot is equal to negative G M1 M2 over, same thing, just R1 minus R2 now. But that doesn't matter because it's just the magnitude, right? R1 minus R2. Now check this out. These masses can cancel, just like this. Mass 2 and mass 2 can cancel. And then mass 1 and then mass 1 can cancel. And then we're finally getting somewhere, right? So anyway, this simplifies to basically this. Yeah, calc is weird. So anyway, let's go like this. What we're looking for again is R2 minus R1, right? That's what we're looking for, R2 minus R1. Yeah, just give yourself time, man. That's what you need. So anyway, what we want is R2 double dot minus R1 double dot. And check it out. We actually have these now. R2 double dot and R2 and R1 double dot, right? So it looks like we've got a negative here, right, that we can kind of throw together. But one of the negatives will cancel out, right, because this negative will disappear. So let's go like this. R2 right here is this. Negative G M1 over R2 minus R1 cubed. R2 minus R1. Okay, and then it's going to be really weird. Then we're subtracting R1, but there's a negative, so we're going to make that a positive. G M2 over R2 minus R1 cubed. R1 minus R2, because it switches up for the other one. Okay, now notice there's an R2 minus R1 and R1 minus R2. We want to put those together, and there's a really simple way to do that, okay? all we have to do is, once again, take out a negative. So r is equal to this. R is then equal to this. Negative g m1 over r2 minus r1 cubed r2 minus r1 minus this time gm2 over r1 minus r2 this time. Again, it doesn't really matter because these are magnitudes, okay? Yeah, I know, Kelly. I know. It doesn't matter though. I mean, you're right, and like as soon as I wrote that, I'm like, somebody's gonna call me out there. No, you didn't miss anything. It's R1 minus R2. You're absolutely right. It's just magnitude, though. It's magnitude, so it doesn't matter what order they're in. But you're absolutely right, Kelly. So, and then this is now going to be R2 minus R1, okay? So now we can combine some terms. But before we combine terms, let's make this a little bit simple, right? First things first, we know a few things, right? We know, but we already know the following. And this is actually R double dot, excuse me. We already know this. We already know A, that R is equal to R2 minus R1. Okay, check that out. We can replace this whole nasty term here with this. And we also know that R2 minus R1 equals the same as R1 minus R2, because it's just magnitude, right, is equal to the magnitude of R, or in other words, it's just R, okay? So with those assumptions, we can make this a lot simpler, and let's do that. Let's make this a lot simpler by going like this now. So now we have R double dot is equal to negative G M1 over R cubed R. Isn't that a little bit simpler? Minus G M2 over R cubed R. Whoa. That's a little bit simpler. Yeah, you got that right. Whoa. Yeah, whoa. It's a lot simpler. Okay? But we can make it even more simpler because there's so many similar terms here, right? We've got this as a similar term. We've got this as a similar term. And we've got this as a similar term. So let's throw everything together. And let's go like this. R double dot. The acceleration of mass 2 with respect to mass 1 is the following. Negative G M1 plus M2, because I'm factoring out that negative, over R cubed multiplied by R. Cool. Whoa. Alright, so right off the bat, this equation tells you a few things, right? This equation firstly tells you, and again, let's take a look. What is R double dot again? R double dot is the acceleration of M2 with respect to M1. Okay, that's what R double dot is. It's how M2 moves with respect to M1. Check this out. We derived this thing right here, right? Which is basically this. Check this out. The acceleration of R, or the place where it's going to be moving, is directly proportional to the position itself, but the negative of the position, right? Let's see if that makes sense. Does that make sense to you? Right? It makes sense, right? So like if your position is going out this way, then the acceleration you're feeling is going the other way. And that's what gravity is. That's exactly what gravity is, right? And I'll put this in layman's terms here. What this is basically saying, and this isn't totally accurate, acceleration will act opposite of position. Okay? That's how gravity works. In the two-body problem, right? Which makes sense. If you jump up, you accelerate back downwards again. It makes sense. Okay, so that's what that equation derives. Now check this out though. What if But what if mass 1 is much larger than M2? If the bodies are very far apart, then the force of gravity on each other instantaneous, or is the pull offset by the speed of light? No, gravity operates at a different speed than the speed of light. It does have its own individual speed, but you can't think of and Eric, I can't give you the answer, right? Because this is research that's actively going on. We do believe that there's a gravitron particle that does take care of things like that, but you can't think of gravity like photon. What gravity does is it quite literally warps space and time. It doesn't send out anything through the space and time plane. It warps space and time. That's what gravity is. Gravity isn't really a force or an acceleration you feel. It's a warp of space-time. That's what gravity is. Well, that's what mass is. Mass warps space-time. If there's a piece of mass in front of you, it's warping space-time. You are warping space-time. That's just what mass does in a universe that has a plane field if massless, right? Mass just warps space and time. So it's a little bit different than just sending out a gravitron. But anyway, there are people that think that there's a propagation speed to that. It's just we just don't really know what it is yet because we don't really have any good examples. So I hope that answers your question to the best ability that I can. But don't think about gravity as a force or like a beam of light. Gravity is quite literally warping space-time because of the existence of mass. That's what gravity is. So anyway, what if M1 is much larger than M2 in this case? Like much, much larger. Well, let's take a look. So if M1 is much larger than M2, then M1 plus M2 is approximately M1. You see that? So we don't have to worry about M2. So get this. If, and I'm saying if, one of your bodies is a lot larger than the other body, then you can ignore the smaller body. No, they don't. No, they don't. It's still up to debate as to what a graviton is or a gravitron. Sorry, no, it's graviton. It's up to debate what it is still. So if we make that assumption, then we can go like this, right? R double dot is equal to, again, it's G M1 plus M2 over R cubed R. All right. Which is approximately Gm1 over R cubed R. Okay? And we're going to put that, we're just going to assume that the mass of your main body then is just G times capital M over R cubed R. Have you guys ever seen this term before? Gm before? I'm curious. If not, what we're going to do is we're going to let Gm equal mu, or gravitational parameter. Yeah, you know it, YOLO. Gravitational parameter. Alright, so if we let mu equal gravitational parameter, and mu is different for every body, well, I'm just going to say planet for now. Different for every planet. It's different for every single planet. Yeah, it's the gravitational constant times mass. You got it. It's different for every single planet. Okay? If we just let that be equal to mu, then we get our final result here. R double dot is equal to negative mu over R cubed times R. Cool. That was not what I wanted. That is the gravitational acceleration you will feel from a body that has a gravitational parameter of this. That's what it is. It's kind of ridiculous how much math we had to do to get there. This was all the derivation behind it. This is not one of Kepler's laws. This was used to later derive Kepler's laws after Kepler already came up with them. We did talk about Kepler's laws, though. We talked about them. But we're on to other things now. This is really just Newton's law of gravitation. That's what this is. But anyway, all this work, and then we finally realized that, boom, if you're orbiting a body, and if your mass is negligible compared to the mass of the body, then you can use this as your equation for acceleration. Nice. Well, I'd say that's pretty neat, right? I don't know about you, but I'd say it's pretty neat. So anyway, we've got that now, which is pretty neat. Let's take a look at one more thing, right? And the other thing we're going to look at is this. Orbital energy. Okay, now there's different types of energy, right? So let's just say your orbital energy. Every orbit has a certain amount of energy, right? It just kind of makes sense, and different orbits have different energy. We're going to call the total energy, in this case, E. Okay? That's going to be our total energy. And our total energy is going to be equal to multiple different things, all right? First off, I guess we should do kinetic energy, right? Because orbits have kinetic energy. Does anybody know the equation for kinetic energy of a particle? And I'm sure, hopefully, some of you guys know that. Funk energy! No, not funk energy. What's up, Bougie? But what is the equation for kinetic energy of a particle with a uniform mass at a point? There it is, Novus. No, YOLO. Kelly. No, not quite Kelly. Novus got it. It's 1/2 mv squared. Yep, you got it. Yeah, you guys all got it. 1/2 mv squared. E equals mc hammer. No. So E equals stuff, right? Stuff. Anyway, there's multiple different types of energy, right? Reward. Can mods... Novus, you might just be able to give yourself space coins. You're a mod. Anyway, so we've got kinetic energy, right? Kinetic energy, which is 1/2 mv squared, right? And then we've got another term, another type of energy you guys may have heard of. What's another type of energy that you have possibly heard of? And no, not funk energy. That would pertain to orbital mechanics. Assume that there is no electromagnetic field around the Earth. Not quite, YOLO. Yes. Potential. Potential. Yes. Novus, I was debating if I was going to show that or not, but I don't think I am. I mean, it's really simple. It's really simple. You can do out the math. I mean, it's just the derivative of this, you get MV. There you go. Mods, you can give yourselves coins. So, cool. Oh, God. I'm going to have to get rid of that function. I don't want my mods using that. I don't trust you guys. I don't trust you guys at all. I just do not trust you guys. It doesn't look like I have the ability to change that. Cool. Okay. Alright. Well, that sucks. That really sucks. Oh well. Oh, I know. No cheating, okay? No cheating. Yeah, Novus, it is cool, man. It's definitely cool. Alright, so, and yeah, we've got potential energy, right? And in this case, we actually do have a potential field that we're working with in orbital mechanics, and it's called gravity, right? Gravity. Right? Nice, Steven Anna. So YOLO, that's actually that's an assumption that you can make when you're close to the surface. But that's not the full equation. And I'm gonna go over how to derive that later, YOLO, but you got it. That is when you're close to the surface, but it's only when you're close to the surface. I'm talking about way far out in orbit, alright? And we're gonna start with this. We're gonna start with force. Get out of my pockets. We're gonna start with force is equal to G big M little m over R squared. Okay? And Bushi. Nice. Anyway, let's take the integral of this force over time, right, which will give us energy. Well, actually, force over distance, excuse me. So we're gonna integrate both sides here. Integrate over distance. No, this is not exactly how you do it mathematically, but guess what? Deal with it. This is another one of the assumptions that I said at the beginning of the night. Deal with it. And I'm not going over this derivation, so whatever. Integral of force over distance is energy, right? So energy, potential, which we're going to call V, is equal to... Yeah, I mean, you have to be pretty close. There's not a cutoff, right? There's not a cutoff. It's just that the accuracy gets worse and worse as you continue to go upwards. Anyway, so that's equal to V, and that's equal to the integral of this, which is just going to be negative G M M over R. Okay? Check this out. You probably recognize this. From all of that derivation that we just did. But anyway, let's put this together, right? So E total is equal to 1/2 mv squared minus gmm over r. Okay? Yeah, I mean, it's the opposite of taking the derivative with respect to r. So it's integrating with respect to r instead. But yeah. So like up here, when you're integrating, you'd have like a dr and then a dr right there when you're integrating. You're integrating with respect to dr. But anyway, we've got this equation for energy total now. And 1/2 m squared minus gm over r. This is total energy, right? What if we wanted a specific energy? Specific energy being... it's energy per mass. Per unit mass. So it's kind of like an energy density, you can think of it as. It's not really, okay? But it's joules. It's joules per kilogram. Okay? It's energy per unit mass. So, what if we divide M by all of these, and we call specific energy, fancy cursive E, right? It's a script E. Well, E is then equal to what? So we gotta take out M here, and we gotta take out M here, right? We're getting into thermo now. No, sorry. It's not specific energy as in like specific heat, specific capacity, or anything like that. This is the astrodynamics version of specific energy. A little bit different. But yeah, I mean same units, I guess. Energy per unit mass then, if we take out mass in both places, we get this. 1/2 V squared minus GM over R. And what does GM stand for? What does GM stand for? What is that term? I just taught it to you. Why are the variables in brackets? Because they're units. Whenever I'm describing something in units, like these aren't variables, they're just units. Yeah, it's mu. So, no putting lows back in the box. Nope, no putting them back. But anyway, it's because they're units. Gravity. General Motors? Yeah, you got it, man. Yeah, it's gravity times mass. I forget who said it, but it's mu. It's the gravitational parameter, right? No, not Pokemon Mew. So anyway, and that brings us to this equation right here. Ready? Specific energy is equal to V squared over 2 minus mu over R. Have you guys ever seen this equation before? And can you tell me what the name of this equation is? Yeah, you kind of are, Novus. What is the name of this equation right here? We've actually gone over it in stream before. I don't know if you guys remember. So close, Kelly, but so far. Mewtwo? No. Bougi's got it. Bougi's got it. This is the vis viva equation. Vis viva equation. Vis viva. It's the living force equation. There we go. Waiting for Mewtwo. Oh my goodness. It's vis viva. Have some candy, Bougie. Have some candy. What the heck is that? What the heck is the living force equation? What the heck is vis viva? That's a great question, man. Every orbit has energy, right? And every orbit has a different amount of energy. But if we put it in terms with respect to mass, like energy per mass... Oh, thank you, Kelly. Anyway, you get this. Energy is equal to V squared over 2 minus mu over R. This is the energy of an orbit, all right? When you hear the term, when you guys all go and work for NASA, you're going to hear this term a lot. When you hear the term energy of an orbit... This is what they're talking about. This is it, right? This is the energy of an orbit. This is the equation. Bougie, well, I'm not giving my mods coins anymore because they can give themselves coins. Bougie, give yourself a couple coins if you want. I really don't care. Guys, the coins are just for like having fun. I don't really care. Except for you, Kerbinot. You take the coins way too seriously. Anyway, that is, when you hear the energy of an orbit, that is what the equation is. So let's take a look at this. Let's take a look at this equation a little bit, right? Let me write it out. E is equal to V squared over 2 minus mu over R. Pretty cool, right? Pretty cool. And there's some equations that we can use to make really cool things come out of this, right? Thank you, Sai. Yes, you do, Kerbin. Now, this is probably the coolest equation you will ever see. There you go, Bougie. There you go. Yes, it absolutely works. Exactly, Novus. This is just sort of like the general state of an orbit. It's just the living force, right? Yeah, well, it all depends with respect to what, YOLO. You gotta remember, right? Way back in this derivation, we assumed that we were doing this. We assumed we were doing it with respect to something else, right? So you have to make sure. You have to make sure that. Give please all hail Bougie. Guys, don't make this difficult. Oh boy. Oh boy. Oh boy. Guys, I want to keep the currency. Currency is fun. So we've got this energy equation now, right? The inflation is real. Buji's the counterfeiter. No, Buji just makes his own money. He's an entrepreneur. Alright. Anyway. We've got this energy equation, right? And we're going to go over a few things, right? So let's go like this. Orbit type is going to be this column right here. And then we're going to go like eccentricity. And then we're going to go semi-major axis. Oh, SMM, no. Feed my... Exactly. Work on it, YOLO. Semi-major axis. And then we now have specific energy, alright? So, you guys are going to help me fill this out, alright? So let's fill out the first column, right? We're going to have a few different types. We're going to have circular, elliptical, parabolic, and hyperbolic. Okay. Tables, you bet. Alright, what do you guys know here? Do you guys know anything? Do you know anything at all? No, seriously, what do you guys know from this? Conic section hype! So what do you guys know here? Oh, hold on. Hold on. Let's see. I need to send a text message. The ovalness, yes. Sounds good, Buji. I don't believe in money. You guys are not helping at all. Jesus, Kelly. There you go, Not Nick. That's a good way of looking at it. Cool. Alright, so you guys got it. In the case of a circular orbit, eccentricity is equal to 0. Right? Oh, sorry, Novus. Novus, you're fine. I saw your comment now, Novus. You're good, man. Oh, man. SMA does sound like a band. Oh, hold on a second. Hold on. Anyway. That's what I said! Yes, it is. It's AYE. She's wondering where I'm at. I'm like, I'm teaching science! Yeah, I know, she should. Did you say 0? Oh, crap. Kelly, you did. Sorry. Sorry, man. You totally did. You totally did. I didn't realize that. You said 0. You absolutely said 0. For elliptical, right? 0 is what? Less than E? But E is less than 1.0. Alright? Not quite. So elliptical is actually a range. Elliptical orbits can take on multiple forms of eccentricity. There you go. There you go, Novus. Yeah, Threnan. There you go. You got a halfway orbit. Good job, Kelly. You made it halfway in life. you get the halfway sticker. Incorrect, Novus. Parabolic orbits are when E is exactly equal to 1.0. Is exactly equal to 1.0 for all parabolic orbits. And then hyperbolic is when E is greater than 1.0. Like that. Yes, you did. So that's what eccentricity is. Let's look at semi-major axis. For circular, right? A is greater than 0, obviously. Right? Dagnabbit. For elliptical, your semi-major axis is also greater than 0. He gets a snow cone. You got it. For parabola, they don't. They only exist in two-body problems, and even then, it would take an ideally infinitely long amount of time to get out there. Because the whole point of parabolic is, as soon as you hit infinity, you have exactly 0 velocity. For the semi-major axis of a parabolic orbit, excuse me, your A is equal to infinity. And then for a hyperbolic orbit, your A is actually negative. Your semi-major axis. All right, now we're going to look at specific energy. Oh. What do you guys think the specific energies are for any of these here? I'm just curious. There you go. There you go, Kelly. Yes, you were. Go you. For what, Mank? For which one? Kelly's got one of them. Kelly just got one of them. It's parabolic, you're right. So for parabolic, your orbital energy is exactly 0. Close, Novus. For circular... Well, for circular and elliptical, the average... Well, I'm not going to go into that. Why didn't I lose? I don't know. For circular, your energy is actually less than 0. For elliptical, your energy is also less than 0. Your energy is negative. Your orbital energy is negative. Hyperbolic, E is greater than 0. Why do you think that is? Why is energy negative when you're in an orbit? Well, the whole idea is that if you're in orbit, that main celestial body captured you. You're in that celestial body's orbit. You haven't escaped it yet, right? If you can get your energy positive with respect to that body, then you get closer and closer to escaping it. And if your energy is positive with respect to the body, or if you're hyperbolic, then that object didn't capture you. You're not in orbit with that object. Well, you are. You're in a type of orbit. But you see what I mean? You're out of it, right? Yeah, like you're trying to escape, but you keep falling. And that's circular. Your energy isn't high enough yet. Yeah, or not far enough. Well, it depends. But hyperbolic, you do have enough energy to escape, and you're going to escape, right? Pretty neat. Pretty neat. Pretty neat, if you ask me. Anyway, there's another caveat here, and I'm not going to go into the derivation. This is the third and final assumption that you can make, where this is equal to negative mu over 2a, which a is, again, a is equal to semi-major axis, right? So let's check this out, and I'm gonna leave you guys with this because it's pretty cool. Let's look at this part right here, right? V squared over 2 minus mu over r is equal to negative mu over 2a. Okay? What's constant here? This is constant. 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 So check this out. If you know... that's integration. It's not like a specific orbit. You can think of that as being a bunch of different orbits at different instantaneous times. Right, so these are all constants, which basically means two things. Two things then. Assuming you know your problem statement, right? Check this out. Well, there's a better way for me to put that, right? This is what Galileo did with Jupiter, right? So, if you know the planet, and know position, then you can calculate, can get velocity. Okay? But here's the thing, you can mix these around, right? So let's go like this. Let's say if you know velocity and you know the planet, right? Then you can actually get position. Now here's where it gets really, really weird, okay? If you know your velocity and if you know your position, then guess what? You know your planet. How cool is that? So and this is what Galileo did. He used an equation that was similar to this. He actually used Kepler's third, and he basically said this: I know how fast these moons are going around because I see them in the sky, and I know the positions in the sky. I know how far away they are. Therefore, I can calculate the mass of Jupiter. That's how he did it. How cool is that? So if you know the position and velocity, then you can calculate your planetary gravitational parameter. How wicked is that? It's pretty cool, right? So anyway, this equation is awesome. You can do a lot of really awesome things with this equation right here. So basically, any of these three parameters, well, in your A, but depending on, A and R are kind of combined there. Those parameters right there, you can just like mix them around. You'll have to send me what you're talking about, Novus. It might be. I'm not too sure. But anyway, check that out. So if it's a combination of any of these things, Pluto's going to be whatever Pluto wants to be. It's not going to be stopped by what humans name it. Anyway, there you go. Vis viva equation. Vis viva equation. You can do a lot of cool things with it, okay? Alright, so, again, we discussed orbital energy today. We derived some things from Newton's law, and we did a lot of other awesome things. I'm going to end it here, guys. I am done. Anyway. That was pretty awesome, right? Yep, and it's in units of joules per kilogram. And if you guys want to look at this stuff, again, I will upload the notes, and you guys will have access to the notes, so don't worry about that. And you'll have access to the VOD, obviously. Alright, I hope you guys got something out of this. It was a lot of fun for me to do. It's always a lot of fun for me to do. Yeah, this was actually a reasonably sized stream. I didn't go for too long, which I didn't want to. Anyway, I hope you guys enjoyed. That was a lot of fun. Catch you guys on the flip side. And again, I'll send out all these notes so you guys can have access to the notes too. So don't worry about that. I will send out the notes so you guys have a hold of the notes. Okay? Alright, well, have a good night, everybody. I am signing off now. So, watching the cutest guy. Oh, get out of here, Not Nick. You're ridiculous. Alright. Good night, everybody. It was a lot of fun.